we're interested just in any isometry, or we may be interested in isotopy. We may consider surfaces, hyperbolic matrix here up to isotopy. But it is strange to just be interested in isometries which preserve only those 3G-3 curves. So the good thing, so we need to be more precise here. Actually, these parameters are not modulo 2 pi, but they should be, if we consider metrics up to isometry, then they should be just real numbers. It is. I try to be careful here and not to be fast, because it is an important thing to understand that if we glue these two components either in some way or in the same way twisted by 2 pi, then the surfaces are isometric. Definitely, since the gluing is the same. But up to isometry on this, up to isotopy, these will be different metrics. And now I would like to explain it more strictly, more rigorously, and to prove it. So this is the main idea. The main idea is, okay, that look, why these two ways to rotate by 2 pi and or to glue just as it is drawn, why they differ? Since, okay, we have here this piece of geodesic which comes to a red point, yes, this geodesic arc. We have, and say we just consider an example when we just glue this endpoint with that endpoint. Okay, we can glue them so that a curve goes as it is drawn here, but we can glue them so with rotation by 2 pi, then this curve goes in some way like that. And okay, if we have some, if we consider this, okay, in some way, if we extend these two closed curves, then these two curves, at least our intuition says to us that they are not isotopic to each other. So we can differ these two metrics from each other. So they are different up to isotopy. So this is the idea, and now let us try to make it rigorously. Okay, to have real parameters, we have some. Okay, even to introduce any parameters, we have some. We need to have some reference point. We need to have some maybe prescribed metric, and then we can measure rotation from this particular metric. So it is convenient to have some base metric, some to start with, and such metric it is convenient to choose it in the following way. It is convenient to introduce the following concept. This concept is concept of seams, since it is not so widespread word. In Russian it's shvы, seams. Seam is shov. So in some way we would like to introduce when we cut these this pair of points into two hexagons, these three arcs are called seams. And now I would like to start with some prescribed set of seams. And I prefer that initially I would like to have these seams to be closed. I would like to consider such situations that we glue these endpoints to each other. So how does it look like topologically? I would like to start with topological point of view, since originally I have no hyperbolic matrix. I would like, next I will construct them. Now, from the topological point of view, look, we would like to have here, in each part, in each pair of pans, we would like to have three arcs. And we would like that they unite two closed curves. So just something like that. Okay. And here here like that, and well, this is an example of seams. Precisely what I require from these curves? I would like to have okay, I have this. First of all, I have these set of cuts which separate surface into pairs of points. And now I would like to have beta 1, beta n. It is not so important how many of them are, but these should be simple closed curves such that they intersect alphas transversally, and in each pair of pans we have this picture. So betas, they disjoint from each other. Betas are disjoint. Beta i's are disjoint from each other. They are transversal to alphas, and in each pair of pans we see this situation, that these are three arcs of beta. Okay, these arcs can be of different betas, or maybe these are arcs of the same beta, or two. This doesn't matter. Just betas intersect this in such way.
Should they have? We don't have a matrix.
We don't have. Yeah. Originally, this is just we keep in mind that later we would like that these are something like this. This will not be completely this theme, these arcs, since we may glue them so that they do not coincide. But this is something related to this. But originally, this is just a topological concept, that just we take a topological surface, we find such cuts, and we find such seams. Why do they exist? Okay, this is very easy. We just take 2 points on each of alphas, and then inside each pair of points we connect them in this way. We have here some freedom. This is not a canonical procedure. We may connect this point to that point, and okay, we have different ways to do this, but at least we can do this. So it's no problem to find for each system of cuts. We can find a system of seams. And now when these two sets of curves, of simple closed curves, are chosen, now our next and the most important thing today is so-called, I just announced that today I would like to introduce Fenchel-Nielsen coordinates. Coordinates on the Teichmüller space. Actually, we didn't even introduce Teichmüller space properly. We say that, okay, Teichmüller space, I recall that I said several times that Teichmüller space is set of hyperbolic metrics on SG up to isotopy. Yes, this is, but we haven't described this as a topological space. Okay, as a set, this is a definition of Teichmüller space as a set, but we haven't discussed its topology at all. But well, main theorem is that this space is homeomorphic to R to the power 6g minus 6, and our goal is to say that to each such set of coordinate curves, if we have chosen cuts and seams, then we can canonically introduce coordinates here. In fact, there are several ways to introduce topology in this Teichmüller space, and not the worst way is just first to introduce coordinates and then to say, okay, that these coordinates give topology. And I will follow this way and then describe, of course, when we do this, the next question arises why the topology is independent on the choice of cuts and seams, but we will prove this. Also, there are more invariant ways to describe the topology, but I prefer to start with this one. And then, so at the moment, this is not well formulated theorem, since we have no prescribed topology here. But our goal is to introduce coordinates in this Teichmüller space and to show that it looks like R to 6g minus 6. Okay, first of all, okay, so further I always suppose that this set of curves is fixed.
Sorry, is it true that this number n can be different for different collections?
Yes. Just look here. Instead of, I can modify this set of seams here. Instead of doing like that, I can do, okay? Oh, no, this is the same. I can do like, and I should move, how can I, well. Okay, and instead of two components, I have just one. I have replaced. So yes, different sets of seams can have different number of components. The set of cuts has always 3g minus 3 components, but here we have some freedom. But I return to the previous ones since it's just somewhat easier to draw. it is by no means better, but it's just easier. Okay. Now, first of all, I have a possibility to produce some reference metric. Suppose that I have chosen lengths for these 3G minus 3 cuts. So I can proceed as follows. I just introduce hyperbolic metric on each of these pairs of points, so that the given cuts and seams are geodesic, and they are orthogonal to each other. So just I would like now to introduce a hyperbolic metric on each pair of paths, so that the prescribed 3 arcs are geodesics orthogonal to the boundary. And there is a unique optoisotropy way to do this. Why? Okay, since we have discussed it yesterday that if we have already chosen these 3 arcs, then we have a unique optoisotropy way to attach a disk. It is always, there is only this metric disk we have only unique optoisotropy way to attach it. So if we found now we do the following. If we are given these 3G minus 3 numbers, then we may produce a metric, hyperbolic metric, in this particular way. We just take these arcs of seams for geodesics are orthogonal to the cuts. So once more, we take each pair of paths, we choose a hyperbolic metric on it, so that the prescribed 3 arcs are geodesic arcs orthogonal to the boundary, and then we just glue them. Okay. Now let us do a slightly different thing. Okay. Now suppose that we have these 3G minus 3 lengths, and also we have additional 3G minus 3 parameters, which are called, okay, these are lengths, and these are twist parameters. And our idea is to glue these two hyperbolic metrics with some twist. A precise formulation is as follows. Okay, I would like to consider one pair of pens, one of these pairs of pens. So let this be one of the pairs of pens. And now, let us consider these are our seams. I recall once more that we are still in topological situation. We still do not have any metrics. I just would like to introduce a metric. So these are just some simple closed curves. No, not simple closed curves, sorry. Some simple arcs that connect these. But I would like okay, I would like I would consider some semi-topological and semi-metrical point of view. So let us consider. We start with this topological situation, yes, and now let us introduce a metric only on these, not on the surface, but we introduce a metric, a length on each of the cuts. So we take, choose a metric on each cuts, and we choose it so that it has the prescribed length Li. So, and that the 2 points which correspond where seams intersect our circle, that they are antipodal. So let us choose the only metrics on this on these cuts. When we have let us formulate this explicitly, that on each alpha I we choose a matrix I will write of length Li, so that intersection with intersection points with beta G's with seams are antipodal. So we consider this as topological surface, but with metric boundary. So and so we have already that these three, and we have lengths on these three circles. Okay, and now I don't want anymore to take these three arcs for arcs which are for arcs for geodesic arcs orthogonal to the boundary components. But I would like to choose new arcs and take them for these geodesic arcs. And new arcs are chosen so that, okay, we travel along the same arc, but we have twist parameters here. Without loss of generality, let this be L1 and 2 and 3. Just it doesn't matter which numbers are here. And consider three twist parameters corresponding to these three curves. These twist parameters correspond to our cuts. And now let us do the following. When we approach this component, when we are in a small neighborhood of it, okay, we are just topologically, we may consider we are in a small cylinder. Topologically, this is just a cylinder. We go left and move by distance θ1. This θ1, if θ1 is positive, if it is negative, then we go right and okay. So we, but okay, this θ1 may be greater than 2 pi, greater than L1. So we can move more than one turn around, or we can move different. But if a different direction, if theta 1 is negative, but okay, approaching here, we displace our point by theta 1. If theta 1 is greater, then we just rotate several times and then arrive to this point. Okay, and similar here, when we approach this side, then we go left and also move by theta 3. This is in some neighborhood, so this is we can just do it in some standard neighborhood. Okay, but an important thing is that we get a new arc, this new green arc. So this red one was arc of sum of themes, but now we have modified it. Modification is prescribed by these two numbers. Okay, in similar way, we modified two others, this arc and that arc. Note that the three arcs obtained are again non-intersecting. Why? The matter is that these two red arcs, they were antipodal. Here we have the same parameter theta 3 for this arc and for that arc. Both of these points are moved by the same length, so they remain non-intersecting. And first of all, they remain non-intersecting, and second, they arrive again to antipodal points. Okay? And similar here. Okay, for instance, here theta was negative, and the result is like that. So this is well defined, and thetas may be positive, negative, greater than 2 pi, any real numbers. This operation is well defined. And now the idea is that we take these new green arcs for geodesics orthogonal to. So now we endow this pair of pans. We endow this pair of pans by hyperbolic metric with geodesic boundary, as usual, with the prescribed length of geodesic boundary, and so that the most important thing, that green arcs, these new arcs, are geodesic segments, geodesic arcs orthogonal to the boundary. Again, we have a possibility to do this. Just we take as I have described last time. We take these two right-angled hexagons, and we glue them to this particular set of. Well, okay, and now we glue these hyperbolic. Now we return here, and this hyperbolic metric. Now we just recall that this pair of pans is not separate. It is somewhere here. So we have made this. We have made. We have made this operation in each of the pairs of pens. Okay. I'm sorry. I made a very small but slight mistake here. A mistake is as follows. Okay, look here. We have this particular seam, yes? When it arrives here, we have, when we approach here, then this green arc moved by some theta, yes? When we approach here, then this green arc moves also by the same theta, but right and left, they change the station. So a usual convention, and it is convenient, that these distances theta. So actually here, it is better to take thetas to take half of thetas here, then the displacement of one one point from another would be theta. So one of them moves by theta to the right, and one of them moves by theta to the left if we look from here, and another moves by theta to the left if we look from there, and so totally they move from each other by each of them moves by theta over 2, so totally we have theta. I'm sorry, it's just some. Okay, so what we get? We get a hyperbolic metric. Now these seams are no longer seams are closed. Seams are red. Curves. Red curves are closed by their very definition. They are called seams. So they are no longer geodesic. Of course, we can consider geodesic representative, but now it is no longer orthogonal to the boundary components. Okay. So, but in other arcs are orthogonal. Okay, what we get? We get that once we have these parameters and that parameters, we have a map which produces a metric up to isotopy. I just described how to produce this metric. We note that this choice of length on circles is not a restriction. We can it is an easy exercise that set of metrics of prescribed lengths on a circle, it's just contractible. We have we can reparameterize it in different ways, but it is not hard to pass from one to another in some canonical way. So so actually our construction is good up to isotopies. So we started from this set of set of numbers. Okay, this belongs to r plus to power 3g minus 3 times r to the power 3g minus 3. These must be positive, and that can be arbitrary real numbers. Starting from this set of numbers, we immediately obtain a hyperbolic metric here. The questions are why these are all metrics and why they are all pairwise non-isotopic.
Yeah, why it is bijection?
Well, yeah, why it is, so the claim is that this is bijection, yes. But we have not proved it yet, bijection. To prove this, we just construct an opposite map. So starting from any metric here, I would like to to compute these 6g minus 6 numbers, and then it would be easy to check that these two maps are opposite to each other. So first of all, so now suppose that we have, I recall once more that we still have cuts and seams, yes? And now we have any hyperbolic metric here. I would like to move another direction. So now let us consider any hyperbolic metric here, not of prescribed form, not no of these curves is geodesic by no means. So just any hyperbolic metric, and I would like to compute these 6g minus 6 lengths. Okay, parameters. First of all, there is no problems with length. Of course, let us do as I just would like to erase something. First of all, there is an isotopy which makes alphas geodesic. Why? We have discussed, we have proved that in each isotopy class of simple closed curves there is a geodesic representative. A good question is why? Okay, for each of these curves we have a geodesic representative in each isotopy class. Why we can find an isotopy which makes all the curves simultaneously geodesics. Okay, but we have already proved this. We have almost proved this. The matter is that we can take any of these curves to a geodesic by an isotopy, yes? Or uniting these isotopies, we get not necessarily an isotopy, but we get a homotopy. The reason is that, okay, these curves, when they move, what is isotopy? It's just our curves move on our surface in some way. When they move, okay, since these are isotopies, each curve remains non-self-intersecting. But they may start to intersect each other if we just unite these isotopies in a naive way. So we get a homotopy, but we have proved that for simple closed curves the homotopy is equivalent to isotopy. And I have claimed, though I haven't proved in details, but this proof can be easily extended to the case of a multi-curve, when we have several pairwise non-intersecting curves. The proof that homotopy is equivalent to isotopy is just extended to these curves, to this case immediately. So this is indeed true that if we have curves and each of them by an isotopy can be taken, can be made geodesic, then they all together simultaneously can be made geodesics by an isotopy of the total of the whole multi-curve. And next, again, this isotopy can be extended to an ambient isotopy of the total surface. And again, we have proved that we can extend an isotopy from a curve to a surface, but the same proof works as well for a multi-curve, just no change. So there exists an isotopy of the identity diffeomorphism. So we start from identity diffeomorphism, then we change it, so that after this isotopy alphas are geodesic. After an isotopy, alphas are geodesic. Okay, and so certainly we just take these L's are just lengths of geodesic representatives. So once more, now we start from a hyperbolic metric up to isotopy, and we would like to compute these numbers. So just Li's are L lengths of geodesic representatives. Okay, and now I would like to compute these twist parameters. Okay, the idea is as follows. Let us start with the following just observation. Just for a moment, consider a cylinder and in this cylinder, suppose that, okay, this cylinder is just a topological cylinder, but we have lengths, as before we have lengths on these circles are metric circles, so we have lengths on these boundary circles. And suppose that we have two arcs here. One arc, this is just simple arc which connects 2 points on the basis of a point on the base of on the upper base with a point on the lower base, and another arc. A natural question is, okay, I would like to ask how these two arcs differ from each other. I would like to consider to allow isotopies of these arcs, which of each of these arcs, which are so that the boundaries are fixed. Okay. It is easy to see that we cannot. Okay. I would like to. Consider such model situation. Okay, we can have that these arcs go in the same way all the way, except and then a red arc goes straight and green arc goes here by moves here by some theta 1 and moves here by some theta 2. The question is, can we extract this theta 1 and theta 2 just if the arcs are not in this position, but we have just two arcs in a cylinder? And the answer is that we cannot. Okay, in this situation, we can make an isotopy of theta 1 so that, okay, theta 1 goes from here to here, twisting once around the cylinder. Okay, we may do as follows. We may go here and then twist around the cylinder. So we change theta 1, theta 2 by the length of the bases. And so in cylinder we cannot read these two parameters from two arcs. But in our situation we have not a cylinder, but we have cylinder with third boundary component. So suppose that we have the same situation on a cylinder with a hole. Then I would like to say that this information, so once more, we have a cylinder with a hole, we have lengths on this and that circles, and we have two arcs. I would like to say that this is enough to compute two numbers, which are twisted numbers. We would like to compute some number here, and we would like to compute some number here, which says how these curves. My goal is to compute these numbers so that if by anisotropy we make these two curves in this model situation when they move along the same line and only then one of them, then we get these particular two parameters. Okay, how to find these two parameters? Okay, the idea is that let this one be alpha 1, this one be alpha 2, and this red, let us choose one of these arcs, let it be gamma. Oh, sorry, gamma is. I claim that alpha 1 cap alpha 2 cap gamma is a deformation retract of our surface. It's very easy. Okay, we have sphere with 3 holes. Of course, this one is a deformation retract of this surface with 3 boundary components. Okay, of this pair of pens. Okay, now there is a very easy but very useful observation. This deformation retraction is canonical up to homotopy. This is very easy since it is a map which is homotopically inverse to the inclusion. So okay, since it's homotopically inverse to a fixed map, then okay, it's unique to up to homotopy. Hence, what? And now let us consider another curve delta, and just take the image of this curve under this deformation retraction. Okay, after this deformation retraction, we have the following. We have 2 circles, alpha 1 and alpha 2, connected by this gamma. We have just this topological space. This topological space additionally with length function here. And now our curve delta goes to the following situation. Okay, we start with, in some point here, we rotate along this alpha 1 in some way, then we go by gamma and we rotate here. Of course, this is not always true. We may go by gamma, then return and go up and so on. But up to homotopy, okay, it is easy to understand how does all these paths look up to homotopy. Up to homotopy, the only thing is that we rotate here move here by some length, go there and move here by some length and arrive here. So we have two parameters: how long we go around this how long I just measure the length, and I measure signed length. So if we go to the left we look from inside. If we go to the left, then it's positive. If we go to the right, then it is negative. So we just get two parameters here. These twist numbers of this pair of arcs. So okay. Good exercise. If we swap the arcs delta and gamma, then these parameters change sign. We could take delta for this base curve, and then if we swap gamma and delta, the twist parameters, change signs. Okay, and now we proceed in the following way. Now, using this observation, I would like to read twist parameters theta 1, theta 3g minus 3 from the hyperbolic metric. Okay, we proceed. We proceed as follows. First of all, I may I can assume that alpha i's are geodesic up to isotopy. I have already said it. Okay, and now consider the following things. First of all, since I have a hyperbolic metric, consider any of these pairs of puns. Any of these pairs of puns. And first of all, these are just alpha 1, alpha 2, alpha 3. First of all, since I have a hyperbolic metric on it with geodesic boundary, then I have three arcs which are orthogonal to the boundary. Well, I would like to draw these three arcs. These three geodesic arcs are orthogonal to the boundary. I draw them by red. But now I can do the following. Here I can change beta i's. I can choose geodesic representatives in isotopy class of SIMS. So I can choose geodesic representatives in the isotopy classes of SIMS. a good question is, okay, is it true that these geodesic representatives again form a set of seams? It may happen that, okay, we take geodesic representatives up to isotopy, these are the same curves, but maybe they intersect alphas in quite different way.
They actually are a set of seams because the intersections numbers should preserve.
Yeah, the intersection numbers should preserve, and here, in fact, it is not hard to observe that again we have a set of seams. We cannot have bigons, so they should intersect these circles in the same order. Okay, we have no way to make it different.
But it's not always that you have the same combinatorial picture. For example, there might be a very complicated seam, and maybe its geodesic representative may intersect in some other way the geodesics are high, or so it's impossible.
In fact, it's impossible. In fact, we always have the same combinatorial picture. But at the moment, let us just notice that this is a set of seams.
When we talked about the set of seams, we said that they have to intersect each pens this way. We will have this property as well.
Yeah, but this is different. 3 arcs.
Yes.
Yeah, we have similarly we have 3 red arcs.
Yeah.
Which they are also geodesics, but they are not orthogonal to the boundaries. So these may be different geodesics. Okay, these are some different. They may intersect each other and so on. These red arcs, they may not meet these circles in antipodal points. There is no reason why they should meet them in antipodal. So just at some points, okay, we have these 3 arcs. No. This is impossible. No bigons, but this is also impossible. I'm sorry. There may be some nasty picture, but not bigons, of course. And these red arcs do not intersect each other. They may intersect green ones, but not each other. Okay, we see something like that. Now, okay, let us call these red ones gamma. Okay, gamma 1, 2, gamma 2, 3, and gamma 3, 1. No, well, corresponding to the numbers of. And similarly, these green ones by deltas.
Sorry, by the way, you told us for definition of the seams that there are no bigons on this picture.
Yes. Seam. What is a bigon? There are no innermost bigon, hence there are no bigons. And no innermost bigon. Okay, but bigon should be contained. Suppose that it exists. It should be contained in some pair of pans. But
Why should it contain a single bigon?
no. We take the innermost bigon so that there is nothing inside it.
Okay.
So it should be contained in one of the pairs of pans, and there are no bigons in a pairs of pans. It's just from the construction. Okay, and so now for each of these 3 for each of these yes, now I would like to compute the twist parameter theta 1. Okay, and here I am interested in how these deltas go left with respect to alphas. Yes, so I need to take, but now I need to remember that there are two pairs of points which meet at theta 1. There is another pair of points here, and here we also have red and green. Here we choose one of the seams that intersect alpha 1. Say this one. Here it also goes. It is for instance 1, 4 to some 1 and some I, and we take and yes, and red arcs, they red curves in this another pair of bands. They red are closed curves, but greens are not. So here we have some different curve, which is delta 1I. It arrives to some different points. Good point. Okay, and now I would like to take the following number. I consider the twist parameter defined in this way. From gamma 1, 2 to delta 1, 2. So this twist parameter in this pair of points. This twist parameter corresponding to this boundary component. For this pair, we have twist parameter at this boundary component and twist parameter in that pair. I consider twist parameter in this particular boundary component from gamma to delta. And in the same way, I consider twist parameter from this gamma to this delta from the opposite side. And I take the sum of them. This is theta 1. Look, this is indeed what we need. This is actually what we need. When we are interested how far these geodesics orthogonal to the boundary are displaced from the curves gamma I from the seams. Here it is displaced by sorry, maybe yeah, it is displaced to the left if you look from here by this one, and it is displaced from to the left if we look from there by this one. Hence we need to sum them, not to subtract, since these displacements add to each other. Okay, and well, there is a good question. Okay, look, to define this number, we choose one of the two seams which intersect this alpha. Yes? We can choose another. We can choose another seam. This gamma 31, gamma 13. Oh, 31 13. It doesn't matter. Okay, we can choose another seam and define this number using another pair. And claim is that the number is the same. I think that okay, I almost should finish. Let it be exercise, and I hope we discuss it during our next part. Well, so exercise that this number θ1 is independent on which seam, which of the two seams intersecting alpha 1 we have chosen. So θ1 is independent on which of the two seams we have chosen. Okay, and now what we get? Let us summarize what we get. Actually, we get these r plus 3g minus 3 times r 3g minus 3. Here we have length parameters and theta parameters, and here we have two maps to the Teichmüller space and back. Actually, I don't want to do it explicitly. It's just a good thing just to think it through, that these two maps are definitely opposite to each other, inverse of each other. So there is nothing complicated here. Just okay, if we by hands, if we took one way, if we took hyperbolic surface and by hands rotate them by theta I, yes, and then this theta I can be measured in this way, and vice versa. So there is nothing complicated here. So they are opposite to each other, and we actually get coordinates on the Teichmüller space. By the way, we have proved an interesting consequence about mapping class groups, which indeed it can be proved easier, even easier, but here we get it by free. Consequence, corollary. Oh, doesn't work. So corollary. Suppose that we have suppose that alpha 1, alpha m are pairwise pairwise disjoint, pairwise non-isotopic, and homotopically non-trivial simple closed curves. Then twists about these curves generate a free abelian group. Then the then twists about them generate a free abelian group. So there is no relations. I mean, in abelian sense, there are no relations among these. It is obvious that these then twist commutate. The an essential claim is that there are no relations among them. Why? First of all, any such set of curve can be included into cut system. We can always add some curves so that cut into points. And then, look, if we make twist around a curve, how do we can act by twist on a hyperbolic metric? How do these parameters change? It is easy. We just length parameters do not change, but twist parameter if we twist along alpha I, then the ith twist parameter changes by the corresponding length. Theta I changes to theta I plus or minus Li, depending on the sign of twist. I don't want to think of signs now. Okay, hence, if we take all, we can take different elements of such kind. Some product of, they all give different metrics with respect to isotopy. Since the twist parameters become different. Hence, they all are different. So we have no relations among them. Okay. And just to finish, I just would like to say, just to announce a fact. Most probably I will not prove it at all during the course, but I think that it is enough beautiful to announce it in any way. Okay, we have different coordinates in Teichmuller space corresponding to different cut systems and seams. Okay, we have plenty of such Fenchel-Nielsen coordinates. It is hard to change of coordinates is rather hard. It is not easy to compute one coordinates from other coordinates. However, there is one thing which is the same. Namely, we can consider the following symplectic form on this Teichmuller space. It is called Weil-Peterson form. It has canonical description, but most probably this will be okay, we will not speak of this during this course, but this is form which is given by this formula. And it turns out that this particular form is independent on the choice of cuts and of the choice of seams. This is some miracle which happens here, and so the claim is that yes. And also to finish, I just mentioned that there are two conventions here. One convention which I use is that these theta i's are when we move here, move the total way around, then theta i's changes by the length. But we can normalize theta I in different way. We can normalize it so that we can just divide theta I by Li and multiply it by 2 pi. So that to get that theta I is something like an angle, which changes by 2 pi when we rotate around. Just I want to say that both normalization are often used. So you may meet one of them, you may meet another of them. The normalization with length is better since this form is independent in this particular normalization, not in the. Okay, but both normalization exist, and you may meet both of them in different books or papers. Okay, I think that now we have a 10-minute break, and then okay, actually I would prefer that we look what the next hour will be something in between a lecture and a seminar. I think I start to tell something, but then we try to discuss it together. Okay, let us make a break. Well, let's resume. First of all, I suggest first to do this exercise. Let us understand why our twist parameter is independent on which of the two seams we have chosen here. Well, let us in fact, it is not hard to see the following thing, that if we make isotopies of these red curves, yes, then we may always, by an isotopy of red curves, we may always achieve that they coincide with these. It is not important. Either we take isotopies of green curves or only of red curves, only of one of these type of curves. We can achieve that these curves, each pair of curves, agree except for some neighborhood of boundary. So let us understand that by an isotopy of one of these sets of curves, we may actually get that here we have such situation that we have red curves and they are green curves. They coincide everywhere except for the boundary, except for some neighborhoods of boundary. And in a neighborhood of boundary, red curves go, say, okay, I would say they go straight, but green curves go in some in some strange way, or vice versa. Actually, it doesn't. Okay. It is more convenient to me to say that well, green curves are arcs orthogonal to the boundary, so it is better to say that green curves go straight and red curves go in some strange way. Okay, it doesn't matter, but still. Okay, but why we can achieve this? We can achieve this for any two of curves, for any of the three pairs of curves, but it is not so maybe obvious that we can achieve this for all the three pairs simultaneously. So that's a question. I claim that we can always achieve this, but I suggest to think why it is actually true.
картинки не могут пересекаться какой-нибудь с кем-нибудь?
Зеленые с красными могут пересекаться без ограничений, а кривые одного цвета никак не могут пересекаться. Но если мы при помощи общей изотопии из непересекающихся кривых получили, мы всегда получаем непересекающиеся. Yeah. Once more, the claim is as follows: that we have we start from any three pairs of we have green arcs between three green arcs connecting the components, and we have three red arcs, and we are interested to make isotopy. We may think that green arcs go straight. Okay, we just call straight. Okay, we can just draw it as straight. Okay, but then it is better to think that I would like to have isotopy fixing the boundary point wise. Yes, of course, and I would like to have isotopy of red curves. So I don't want to change green curves, but I would like to have isotopy of red curves so as to achieve the following: that red curves out of some small neighborhoods of the boundary components, red curves coincide with green curves. So they go straight, and in these neighborhoods something happens. Actually, in these neighborhoods, okay. First, let us understand that this is enough. If we do this, then this exercise will follow. Let us start with this. What can happen in this neighborhood? Here we have a neighborhood. It's just a cylinder. We have two antipodal. Here and here we have two antipodal, just straight green segments. And we have, yes, in the cylinder, let here be the our pair of points is from this side. So this is the boundary component alpha I. How does this red curve look like? Okay, it is just some curve in the cylinder. It just can rotate maybe by several turns and so on, and to arrive to same point. Okay? Another red curve goes from here to some point here, and it goes non-intersecting the original red curve. These two red curves don't meet each other. And we have here we have another pair of pans, and here we have a cylinder, and we have a similar picture. Yes? Now let us consider, but okay, a similar picture. Red curves are continue each other, so they meet in the same. But green curves, they meet in some different way. Okay, something like that. Now let us cut this cylinder and look on its universal cover. Not the universal cover of the whole surface, which is maybe something complicated. But I just would like to cut this cylinder and look on its universal cover. How does its universal covering look like? It looks like very easily. It's just a strip divided by this alpha I into two parts. Okay. Here we have these green segments, and they are okay. Let this green segment goes to the second, and this goes to the third. We have two different grids, so they are 1 2 1 3 1 2 1 3 and so on. They go in some order. Okay, here we have similarly. Okay, let it be 4 and this one be 5. Okay. Similarly, we have green segments in such way that go that eventually goes to 4 and to 5, but I consider only those parts which are inside the cylinder. Okay. Now let us look on how does yes, and I would like to go to look on one of the seams. Yes, so suppose let 4 be those to which a seam from 2 goes. Yes, one seam starts from 2 and goes to one of these 2. We may assume that it goes to 4, and those which start from 3 goes to 5. Okay. So we have here something like that. This curve starts from 1 2. It goes in any it may go in any way, but finally it arrives to some 1 4. Okay. So the twist parameter which we see here we have 2 twist parameters. This is one of them, from this one 2 to this one 4. Okay, we look we look on how the red curve differs from these green straight curves. This is exactly our first, and the second parameter is this one. We look on this situation. So the sum of them is in fact на английском, к сожалению. The sum of them is this segment. Well, so in fact, it is not important where this red curve meets the middle line. It is only important that it goes from here to here. We just need to take this length, with corresponding sign, of course. Okay, and now another red curve starts from here. This is the second one, which goes from 1 3 to 1 5, and finishes in one of these 5s. But in which of them? Of course, in this one. Since here, if we start this red curve, okay, it has a copy which starts from here. It is just a parallel copy, and it goes to this one. And since these red curves do not intersect each other, the curve from here may finish only in this particular 1 5. So the distance will be the same. Yes? And this is exactly what we need, that this twist parameter is independent on so we again arrive to our questions, why we can do all these curves trivial out of some small neighborhoods. Maybe, well, in fact, I don't want to spend time on this. It is there is almost no need to think in this problem, but there is need to. We need just to draw and draw and draw. Actually, the idea is that we just simplify one of the curves. There is no problem with it, just by means of those deformation return. Then we cuddle on it and look on what we get, and on that polygon we slightly think and get something. I suggest you try to do it yourselves. So I don't think that this should lead to some difficulties. Okay, so we may think that we have finished the proof of this theorem. Now let us. Yes, I would like to say some words about another more classical point of view on the Teichmüller space. There is another origin for the same topology. So once we have proved this, we obtain a topology on the Teichmüller space. One question is why this topology is independent of the cut system and seam system. It is true, and I hope we can discuss this today, but first let us start with another source of topology. We may obtain topology from a more algebraic source. We can look on hyperbolic metrics in the following way, that if we have a surface with hyperbolic metric, then once more it has a universal covering, and we have discussed that this universal covering is just the Lobachevsky plane, the whole Lobachevsky plane, and so our original S is the quotient of this Lobachevsky plane by the group of deck transformations. This is some group of isometries, yes? But this group of isometries of the Lobachevsky plane of orientation preserving isometries. I just once more I recall that the group of orientation preserving isometries of the Lobachevsky plane, it is first of all the connected component of of this pseudo-orthogonal group, yes, and on the other hand it is PSM2R, since it's the group of orientation preserving the group of linear fractional transformations that preserve the upper half plane. Yeah, this is the group of isometers in the upper half plane model. Okay, and now look, that this group of deck transformations is of course isomorphic to the naturally isomorphic to the fundamental group. So actually, looking on this picture, we get a representation of the fundamental group of the surface to this group PSL2R. Okay, but now let us look on this construction. Okay, we take hyperbolic surface, we consider the universal covering, it is isomorphic to the Lobachevsky plane, and we get a representation. Yes? So starting from hyperbolic surface, we have produced a representation. But now let us look on which choices we have made. So up to which extent this is canonical. Yes. But before doing this, let us start with two simple notes: that this representation is discrete and faithful. Discrete means that this subgroup goes to a discrete subgroup of PSL2R. Okay, so since the group of deck transformations must be discrete. Otherwise, no good quotient existed. So this one should be discrete. And faithful means just that it is injective. And of course, again, since it's a group of deck transformations, it must be faithful. So, starting from hyperbolic metric, we get a discrete faithful representation of the fundamental group. But now, how canonical is this construction? Actually, we have here only one step which is not canonical. This one. We have this isometry, but this isometry is not canonical. But it is unique up to an orientation preserving isometry of the Lobachevsky plane. Okay, so and of course, if we choose this one in a different way, then the representation will change to a conjugate representation. So actually the picture is as follows. The group PSL2R, the group of isometries of the Lobachevsky plane, acts by conjugation on discrete faithful representations of P1 of SG. Well, so just I would like to have more space. So let us consider the set of all discrete faithful representations of P1 of SG to PSL2R. And we take the quotient of this set by PSL2R, which acts here by conjugation. Okay? And now look, starting from a hyperbolic starting from a hyperbolic surface here, we get a discrete faithful representation. Yes? Vice versa. suppose that we have a discrete faithful representation of the fundamental group. Then we can take the quotient by it and we get a hyperbolic structure. Yes? So this correspondence is one to one. Yes? So this is a one-to-one correspondence. Okay, and now the question. Do we get here a Teichmüller space or the modular space? So do we get hyperbolic matrix with which equivalence relations? So we get hyperbolic matrix on SG, but what is the equivalence relation? Is it isotopy or isometry?
Isotopy, since we fix on the left hand side we fix V1, so we remember which
Yes, actually, we remember how our surface is identified with this one. So this is just this is by isotopy, and this is just a Teichmüller space. Okay, and this thing has a natural topology. Now, okay, this is a very important bijection, yes, and now here we have a natural topology. Namely, we have, okay, PSL2R is just a topological group, it's a Lie group. This one is discrete, and we have usual compact open topology in this space of representations. Just as usual, set of maps is endowed with compact open topology. So we endow here with compact open topology. And we take the quotient by PSL2R. Okay, we get a quotient topology. The quotient topology on this, on the quotient. So this one is endowed with the quotient topology, and from this point of view, it is not easy to see that this is an R6G minus 6. But on the other hand, this topology is canonical. It doesn't require any choices. And actually, this is an exercise which I definitely don't want to discuss on the blackboard, since okay, it's completely technical. It has no ideas, more or less. The exercise that, okay, this topology coincides with the topology coming from Van Helmholtz coordinates. This topology coincides with the topology coming from the Van Helmholtz coordinates. In particular, it follows that the Van Helmholtz coordinates corresponding to different cut systems and to different seams, they are they give the same topology on the Teichmüller space. Well, the idea is that, okay, if we slightly disturb a representation, then all geodesics also change slightly, and we can follow through the whole proof, and we can go through the whole proof and understand that all parameters change slightly. Well, so the idea is very simple, that if we change slightly the representation, then everything changes slightly. But technically, we need to go through these steps, and it is very unpleasant to do this on the blackboard. And vice versa, if all parameters change slightly, then the corresponding isometries also change slightly, and we get close representation. So this is more ideologically, this is more or less obvious, but if we try to write it down with all details, it may be long. Okay, and now I suggest yes, and another important thing is that if we pass from one, suppose that we have two different cut systems, two different system of seams, and we pass from one Fenhill-Nielsen coordinates to another one. Okay, from this picture we can see that this, when we pass from one to another, this is homeomorphism. But actually this is diffeomorphism. This is smooth with all derivatives, and a natural question is how to understand this. This thing is not very good from smooth point of view, since we have some factorizations, and taking quotients sometimes works badly from smooth point of view. But okay, actually again I will say an idea, and I hope you may think it's through yourself. Well, the idea is that, okay, suppose that we have one cut system, and we have also we have a set of seams, but I just to say an idea, I just don't want to draw it down. And we have another cut system, and for instance, one of cuts is something like that. This is one of cuts in another cut system, and we are interested in the length of the geodesic representative. So we would like in the first Nielsen coordinates are like that, and we are interested in let it be alpha 1 prime, the first curve in another cut system, and we would like to go here to change the coordinates. And let us discuss why this L1 prime depends smoothly on all the previous ones. The idea is more or less the following, that this alpha prime cuts several curves in in certain order. Yes? May this order change if we change the... I take the geodesic representative here. May this order of patterns change if we change the hyperbolic metric? The answer is not, since it always must be transversal. And our Teichmuller space is connected. So if we change the metric, then the topological picture cannot change. So we have always here several points. Which parameters are here? We can points here, we can angles here, at which we intersect these parameters. What does it mean, points here? We have pre-chosen points where these reference points, yes? And we have signed distance to this point, and we can say, okay, this geodesic representative, it meets those geodesic representatives at some points given by some parameters, and it goes at some angles. If we knew these parameters and these angles, then we can compute these lengths just by some trigonometry. So this is some planimetrical question in a right-angled hexagon. We can write this formula and so on. And now all these parameters, if we change this parameter, then the lengths of the segments vary smoothly. And so it's something like implicit function theory, that these parameters also depend smoothly on the hyperbolic metric. And so something like that, we can just write these equations, show that implicit function theorem can be applied, and do it. So here again, ideologically, it is not hard that we have here a diffeomorphism, but it may be long to fill all details. Okay, but in the rest time, let us discuss some easier questions. For instance, suppose that we have a closed genus G surface with a hyperbolic matrix. A good question, which is often needed, is the following. Is it true that there are only finitely many simple closed geodesics of bounded length? So suppose that we look on a hyperbolic surface with the hyperbolic matrix, and we are given some constant C, and the question is it true that there are only finitely many simple closed geodesics of length less or equal to C? This is the first question, but maybe a slightly more interesting question is we can vary hyperbolic metrics, but take the same C. and ask whether the number of closed geodesic is bounded by some function of C. So is there the same bound, okay, dependent of C, of course, for all hyperbolic metrics? Is there a uniform bound? Why, before discussing these particular questions, I would like to describe why questions like that, why questions of such kind are important. Namely, there are plenty of complexes on which the mapping class group acts, and often the idea behind such complex is the following: that okay, it is always if we study a group, then philosophically it is always useful to have a good action on some cell complex. It helps us to understand a group. But it is much better than if we have an action on complex such that we know something about topology of this complex. Okay, it is good to have an action on a connected complex. It is better to have an action on simply connected complex. It is very good to have an action on a contractible complex. So if we know something about the topology of a complex, then it is very good and convenient to us. But it is okay, a natural way to construct complexes with good properties is to make some ideologically some points of these complexes, something in these complexes should, some parts of this complex should correspond to some points in Teichmüller space. We know the topology of Teichmüller space. It is contractible. And this is deep result. This is not an easy result. It is not something obvious. But now, since we know, it is good to use the topology of Teichmüller space to understand something about the complexes where the mapping class group acts. And now, suppose that we have a point of a Teichmüller space. It is a metric on a surface. It is very natural to look something like the shortest geodesic in this metric. And we get some curve. Maybe it is not unique, so we may get several curves and so on. But something like that, the shortest something, to minimize something, or maybe not necessarily geodesic, but if we would like to minimize something, then always we have questions like that. Is there finitely, maybe there is not the shortest geodesic. So at least we would like to have a shortest geodesic. And often some compactness arguments like that are useful. So let us try to discuss this. May it happen that there are infinitely many geodesics of bounded length. If not, then...
Well, if we are thinking about like something like flat torus, but of course it's not...
Yes, in flat torus we have infinitely many of them, yes. But we have only finitely many isotopy classes of them.
Yeah.
Here, there is no difference between isotopy classes and representatives, since there is a unique geodesic representative in every isotopy class. So let us at least try to find which ideas can help in solving this.
I think that we can start by looking at what homology classes they represent.
Okay.
Можно взять какие-то отрезок на части, а потом понять, что мы условно говоря, сколько там можно сделать разрез, не пересекающий, остальные должны пересекаться. Если он пересекает, значит он должен найти одной
Yes. A good idea is as follows. Let us take, for instance, again a Pans decomposition. Yes? So say this one. This is just an example. Okay. If we have a hyperbolic metric here, then for each pair of Pans, take a pair of Pans and take two of components. Yes? Then there is an arc, which is the shortest path from this to this one. Yes? And we may consider all these lengths, epsilon i's, all lengths of such shortest arcs. Okay? And we may take the minimum of them. Yes?
Yeah.
And now, if our curve intersects let us take any curve and put it in minimal position with respect to our cut system, to our red curves. If it has k intersections, then it has k segments between them. Each segment must have at least this length. So what we get? We get, okay, let this cut system be alpha 1, alpha 3, g minus 3, and let this curve be gamma. Then we can get that the length of gamma is greater than or equal to epsilon times the sum of geometric intersection index of gamma with alpha g. Okay?
Yeah.
Does it solve our question? No, not yet. Yes, but at least concerning homology classes, we get some restriction. Yes.
Yeah.
We cannot, since homology class prescribes algebraic intersection indices. Yes, not geometric, but geometric are greater than the absolute value of the algebraic. So if a homology class have if it has big algebraic intersection indices with these components, then we definitely have a big number here. Okay, does it follow that there are only finitely many homology classes? So we are given C. Does it follows from what we understood that there are only finitely many possibilities for a homology class of a geodesic of length smaller than or equal.
Not immediately.
Not immediately,
Because
but
again, if you think about like just torus, you can or like one cut, and you can spin around it, and you have just one intersection with it, but you add the orthogonal homology class.
Yes, there are plenty of homology classes which have very small intersection indices with these homology classes of these cuts. And how to understand at least that we can take finitely many homology classes.
We can take different cuts.
Yes, we can take different cuts. These cuts always generate, in the homology group of SG, these homology classes of these cuts generate a Lagrangian. What does it mean? They generate a direct summand with of rank G with trivial such that the intersection form vanishes on this summand. Say we can take some G of these cuts, some G homology classes of these cuts. We can take for A cycles for A1, EG. And then finds some B cycles, yes? Okay, and then looking on this particular cut system, we may say that, okay, any homology class is sum of A cycles plus sum of B cycles with some coefficients. Any homology class has such form. This cut system gives us the following restriction, that the sum of these indices cannot be large. If it is large, then the intersection indices with these cuts, with the corresponding cuts, becomes large, and we have large number here. So these are bounded, these MIs are bounded. Another cut system with which that generate a complement Lagrangian subspace given by B cycles. And this new cut system, it has its own epsilon, maybe different one, but still we have only two such cut systems. We can take the smaller epsilon, and we again see now that these NIs are bounded. Okay, so homology classes are bounded, but in any homology class there can be infinitely many different representatives.
Я запутался. У нас этих разрядов исключение минус 3,
Да.
а в среднем homology у нас раза 3 минус.
Не, эти, конечно, линейно-зависимые гомологические классы. Некоторые же из них можно выбрать за аиты. Ну вот, скажем, этот и этот. Да, не, их, конечно, слишком много. Окей. Okay, are there any ideas how to deal with homotopy classes instead of homology classes?
If we have cut the surface into disks and say that the geometric intersection indexes of the cut is bounded.
Yes. Okay. For instance, this can be done. This can be done in many equivalent ways. For instance, we can take. At least I like to do this as follows. We take cut systems and that seam system. Okay. We have these cut systems. I just draw an example. We have cut systems and we have seam systems. And this one. And they together decompose our surface into disks. Yes? If a curve has small length, bounded length, then its geometric intersection indices with all curves drawn here should be bounded. Yes? Since otherwise this seam system also can be included into a cut system, and we have estimate of such kind. Okay?
So that it seems like a
Yeah. We took geometric representatives of these seams. In any homotopy class, we can take geometric representatives. Okay, now, so say we can all geometric. These are alpha i's, beta j's, and we have some curve gamma. Suppose that all intersection indexes of gamma with alphas and with betas are bounded by some n. Okay, we understand that we have such bound for certain n. What can we say? Okay, we have not more than n intersection points with each of the curves. Now we have finitely many ways how these intersection points, okay, we can have 5 points here, 4 points there, and on different, they may lie on different segments with different, maybe different numbers of, but we have finitely many of them. Since there are in total not more than 1 million points, then we have finitely many possibilities to put these points on segments. And once we have put, okay, now look on each disk here. We have some disk, and we have finitely many points where gamma intersects this. Okay? Now we need to divide these points into pairs so that the picture becomes non-self-intersecting. Okay, I didn't succeed to do this, but something like that. Okay? Again, there are finitely many ways to do this. Since there are finitely many. And not every such way gives us a curve. Since sometimes we may connect it, but we may get many connected components. But sometimes we get a curve. But okay, at least we have only finitely many possibilities. This answers A, but this doesn't answer B.
Sorry, but do we use this curve with simple clause? I mean, maybe we don't have in the...
Yes, it is a good. Thank you very much. In fact, it is completely. It is not important that this is simple closed. It is true as well for all geodesics. So, okay, if it is not simple closed, then here we may have self-intersections, but there are still finitely many of possibilities for them. Okay, but okay, maybe this B may be considered as a home task, so we may skip it now. We have only 10 minutes. Let us discuss another important question. Okay, is it always true that there should be a short geodesic on a surface? Is it possible that all geodesics, vice versa? Here we say that there are finitely many short geodesics. But is it true that there should be a short geodesic, a rather short? May it happen that all geodesics are very long? Note that geodesics in a cut system may be very long. We can have arbitrarily large lengths for all these geodesics. But is it true that so the question is as follows. Given the genus, does there exist a constant such that any hyperbolic surface of genus G has a geodesic of length smaller than CG. Okay, smaller. This is A, and B maybe if yes, then does CG depend on G? Is it possible that there is some bound which works for all surfaces simultaneously? So this is not very difficult question, but let us discuss it. Yes, here returning to this question, I just would like to say that this is actually true. Or, sorry, in fact, I don't remember whether it is true or not. Okay. Yeah. Okay, let us discuss this easier question. Can we have, say, a surface of genus 2 such that all geodesics are greater than 1000?
Там, скорее всего, если делать то же самое, если у нас есть длины очень большие у консистом, тогда если соединить серединки, то длина будет достаточно маленькая.
Yes, one way to answer this question is that take a cut system and consider here this one particular pair of pawns. Yes? Then if we cut it into two right-angled hexagons, then these lengths corresponding to these red curves are very large, these three. And using the cosine law, it is easy to see that three other lengths are very small. We can, if three lengths are large, then three others are small. And we can write down these estimates explicitly, and hence it is rather short to go from one point to another. And now we can take a homotopically non-trivial curve of rather small length. It is not geodesic. We just go by. But no. It is not so easy. We may go here, but we have small arc here. We have small arc here, but their endpoints are may be very far from each other.
Я предлагаю идти из серединки в серединку по какой-нибудь кривой, правда? Потому что это там неправда даже.
Yeah. No, this doesn't work. I wanted to say that okay, this works, but we have an easier way, but this doesn't work.
Сейчас эта константа, она должна зависеть как-то, ну вот, от чего она может зависеть, от того, там, сколько мы подштанов разбили, да, и вот как-то там накатали какую-то оценку. Ну, если там есть.
Well, actually, I should give you this question before we discussed pairs of pawns, and then it would be much easier. This is a rather simple geometric questions. Pairs of pawns are much harder than this question. Well, so there is one thing which is the same for all hyperbolic metrics on the surface. It's the area of this hyperbolic surface. The area of any hyperbolic surface. We have a Gauss-Bonnet theorem.
It's proportional to the orbit fluctuation.
Yes, it's 2 pi minus 2 pi times the Euler characteristic. So it's 4g minus 4 times pi. Okay? It is fixed. Now suppose that what is the, now we have this Lobachevsky plane, which is the universal cover of our surface, and some group acts by isometers here. Okay? Suppose that this group has an orbit with 2 points some element of this group, some deck transformation, takes this point to that point. What? Well, what does it mean? It means that in the base we have a loop of this length, which is distance from x to y. Yes? So if we have no short loops, yes? Then if all loops, yes, and this loop is necessarily homotopically non-trivial, since its lift is not closed. Yes? If all homotopically non-trivial loops have lengths greater than c, yes? Suppose that.
Yeah.
Then our group of isometers cannot have 2 points in the same orbit on distance smaller than c.
Yeah.
Okay? So any 2 points, if 2 points are on distance smaller than c, then x and y in different orbits.
And we can take a ball.
Yes, we can take a ball of radius c over 2, and all points are in different orbits. Hence, the area of the surface is greater than the area of a ball. But the area of a ball tends to infinity if the radius tends to infinity, and we can easily write down how it tends to infinity, and actually from this we can get some estimate for this constant. Okay, and so this finishes part A. Okay, and what about part B? May we have here a constant which is
By this construction it does.
yes, by this construction it does depend on the genus.
You can write the right like unbounded.
Yeah, of course, area grows.
We might try to take a regular for G1 and see if that sure.
Yes, the answer is negative. If we take a regular for Gigon with, we can always glue a hyperbolic surface. This was our first construction. We can take a regular for Gigon with angle pi over 2g and glue a surface. And it is not hard to show that the shortest geodesic would be in this particular surface would be its edge. And this edge also, it is not hard to show that this edge tends to infinity as g tends to infinity. However, it may be shown even easier that the answer is negative. The matter is that if we have
Even the answer is positive.
the answer is it depends. We cannot take this g independent of g. Namely, if we have any hyperbolic surface, then we can choose a shortest geodesic, and we can take, say, a twofold covering which duplicates this shortest geodesic. And this particular geodesic becomes longer. From this thing which we have proved, it follows that we can have only finitely many short geodesics, and hence then they can be killed by such coverings. So we always can choose coverings. And it is important that actually this construction can be made more easier and more natural by the following way. We can do it. It is also useful argument that we can take here this group of consistent of all isometries. Instead of saying about covariance, we can say about subgroups of finite index. It is the same, but it is sometimes easier and more convenient. Okay, if here there is an isometry, there can be only finitely many of isometries which take a point to a rather close point. Since all these isometries are in some metrics in this group are on finite distance from the unity. So we can kill them one after another by taking finite index subgroups, and so to get a surface without small geodesics. Okay, let us finish for today. So,
Сразу, да?
да.